My name is Jason Gers, and I'll be presenting on relativistic dynamics and how my partner Thomas and I tested relativity and determined some properties of the electron. The goals of our lab and of this presentation are to test relativistic dynamics against classical mechanics, against Newtonian mechanics, to determine the mass and charge of the electron, and I'll be diagnosing any systematic errors that pop up. Special relativity is a theory about fast things, things moving very, very quickly. It predicts that things moving quickly undergo length contraction. They get shorter, or apparently shorter. Time dilation, we see time move more slowly for things moving quickly. And most importantly for this experiment, there's a universal speed limit of the speed of light. Relativity says that nothing can go faster than light. So why do we care about testing relativity? My personal answer to this question is because relativity is awesome. I think that relativity is one of the most interesting theories in all of physics. If you want a more concrete answer, relativity is required to understand things moving quickly. The most famous application of this is GPS satellites. For an order of magnitude estimate, if you neglect special relativity in doing GPS calculations, your calculations of where you are based on the GPS satellites will drift by about 2 kilometers a day, which is completely unacceptable for things that need to guide you to within a few dozen meters. So how do we test relativity? Well, you move really, really quickly. Or you find something moving really quickly. What moves quickly? Light is the first thing that comes to my mind is something moving quickly. In fact, relativity predicts that nothing can move faster than light. But light is fairly hard to do relativistic tests with. So we won't be using light. Instead, we'll be using electrons. Electrons are lightweight, and this means that it takes much less energy to get an electron moving quickly than, say, to get a proton moving quickly. Our source of high-energy electrons will be the radioactive element strontium-90. When it decays into ytterbium, it releases about half a mega electron volt of energy. This is enough to get an electron going at about 80% the speed of light. Ytterbium decays, this time releasing about 2 mega electron volts. And this is enough to get an electron moving at about 97% the speed of light. So our electrons went very, very quickly. In order to test any theory, you need points of contact between the theory and reality. And we have 3 points of contact in this experiment. There's the momentum of the electrons, the force exerted on the electrons, which is the time derivative of momentum, and the kinetic energy of electrons. And I'll come back in a short while to exactly how these are points of contact between the theory and reality in this experiment. This is a picture taken from the lab guide of the experimental setup. Over here is our source of high-energy electrons. The electrons are emitted here. This entire circle represents a spherical magnet that creates a uniform magnetic field perpendicular to the screen. When charged particles move with a constant speed in a uniform magnetic field perpendicular to the direction of the magnetic field, they move in circular paths. These are the paths of the electrons. The fact that they're moving in circular paths means that we can select for certain radii by sticking a barrier down the center of the spherical magnet and only letting electrons that are traveling in circular paths of specific radii through. The reason that selecting for specific radii is useful is because these are the equations that govern their motion in this region. We have that the force exerted on the electron is proportional to the charge, the velocity, and the magnetic field on one side, and on the other side it's equal to the angular speed cross the moment, or angular velocity cross angular momentum. And after a little bit of rearrangement, you get that the magnetic field is proportional to the momentum and inversely proportional to the charge in the radius. And this means that if we fix the magnetic field and the electron charge is fixed, by selecting for a particular radius that allows us to pick out electrons of a particular momentum. The electrons that have the approximately appropriate momentum make it through the barrier over here. They get to the velocity selector up here. The velocity selector is a parallel plate capacitor. It has a constant electric field between the two plates. And how this works is that if we set the velocity selector such that the force exerted on the electrons by the electric field precisely cancels the force exerted on them by the magnetic field, then those electrons will go straight through the velocity selector and impact on the pin diode, which is how we counted our electrons. All the other electrons will either experience more force from the magnetic field or the electric field, and so they'll be sent into one of the two plates and won't make it to the pin diode. The specifics of how this works are governed by this equation, that the force is equal to the sum of Q times, or charge times the electric field, plus QV cross B. And after some rearrangement, you get that beta, which is the velocity over the ratio of the velocity of the electron to the speed of light, is equal to the electric field divided by the magnetic field, scaled by the speed of light. So after the appropriate electrons get to the pin diode, we get a signal that's proportional to their energy for every single electron, and so we can both count the number of electrons and we can get a count for and we get a reading of what energy each electron has in some units. So the predictions of the two theories of classical mechanics says that momentum is equal to the mass times the velocity. Relativity says that momentum is equal to gamma times the mass times the velocity, with gamma, this constant, 1 over the square root of 1 minus beta squared. If you do the manipulations and plot these are the two curves that you get. Classical mechanics predicts a straight line. The dashed lines are error bars on the two curves due to the fact that we don't know exactly what the radius of the spherical magnet is. And here you see the relativistic curve, which limits to a value of beta equals 1 of things going at the speed of light. The magnetic fields that we used ranged from 80 Gauss to 120 Gauss. So in this range, you see that classical mechanics predicts things going at around the speed of light to well above the speed of light, and relativistic mechanics predicts things going going below the speed of light. So here they differ significantly. In order to, so I said before that there's a particular value of the electric field that precisely cancels the magnetic field for electrons going at a particular momentum. In order to find that value, we took broad sweeps of how many electrons got through the velocity selector at various electric fields. And these are the results of those broad sweeps from 80 Gauss up to 120 Gauss. You can see that they're approximately Gaussian. I fit these to normal distributions and looked at the peak values. I assumed that the peak value was, or the most probable value, is the value where the electric field precisely cancels the magnetic field. When I took this data and I manipulated it and plotted it, this is the result that I got. You can see that the data is clearly relativistic. Relativity wins. There's also clearly a systematic error. The data are somewhat below the relativistic line. We can ask, how far are we off? How bad is this systematic error? And we can also ask, are either of these actually good models? Because large offsets sometimes hide systematic distribution problems. So first, how far are we off? It turns out that the only place that electron mass and charge show up in the equations that I used are as the ratio E over, or charge over mass. When we use this as a fit parameter, I got a value of about 1.55 plus or minus 0.02, all times 10 to the 11 coulombs per kilogram. compare this with an accepted value of about 1.76 times 10 to the 11 coulombs per kilogram. We're about 10 sigma off. So this is pretty bad. Are these good models? This is a fit for the classical model. If we assume that the book values of electron mass and charge are completely wrong, and that we think maybe the electrons are actually behaving classically, this is the fit that we get. The residuals are very clearly systematic. So no matter what you do with electron mass and charge, these electrons are not behaving classically. The relativistic fit is a lot better. Reduced chi-squared is 0.3. The residuals are still systematic, though. This is possibly the same error as the systematic offset that we saw before. We can ask, what causes this systematic error? The parameters that we have are the radius of the spherical magnet, the separation between the plates, the voltage that we set on the parallel plate capacitor, and the magnetic field strength. We can use each of the constant ones of these as fit parameters to see if that fixes things. And we can check, say, linear offsets for magnetic and electric field. If we think that the error is caused by the wrong value of the radius, I use that as a fit parameter. The residuals are still systematic, so that wasn't the problem. If you use plate separation as a fit parameter, the residuals are no longer systematic. That's looking pretty good. Reduced chi-squared is 1.1. That's also pretty good. But the offset is about 0.01 centimeters, which is 3 to 4 times the uncertainty given in the lab guide on the separation between the plates. That's not so good. If I assume that the magnetic field was off in some linear fashion, that there's a constant offset and also a scale offset, this is the fit that I get. Again, the residuals look not systematic. Reduced chi-squared is tiny. The change in slope is about 0.05, or sorry, 0.06, which corresponds to an offset of about 6 Gauss at 100, which is approximately where we were looking at. And the constant offset is is about 2 plus or minus 4, which is approximately negligible, or approximately 0. If we do a fit for V, we get similarly non-systematic residuals, similarly small chi-squared. And so doing these doesn't let us distinguish between plate separation, magnetic field, and voltage. But we have another point of contact with reality in this experiment. We took readings of the kinetic energy of the electrons. Classical mechanics says that kinetic energy is p squared over 2m. Relativity gives this more complicated formula. And recall that the momentum is equal to BE rho. So here we have that the kinetic energy is only dependent on B of the 3 things that we think might be causing the systematic error. So if the systematic error shows up in the momentum energy plots, then it means that it was caused by an error in the magnetic field. Otherwise, we have to look for something to distinguish between plate separation and voltage. When we plot these, this is what we expect for classical and relativistic. In order to get the energies, the actual energies, we needed to do a calibration. Here's a plot of what the barium-133 spectrum looked like in this detector. And this is the calibration that I did, linear calibration with the 6 most prominent peaks. Here are the energy peaks for each of the electric field, magnetic field pairs. And when we plot the data, we get this. So there's a systematic error here. And again, it's clearly relativistic. So that means that the error was caused by the magnetic field. Finally, using this model, these data, we can calculate the electron charge and mass. When we use those as fit parameters, this is the fit that we get. We get a value for electric mass that is within 1 standard deviation of the accepted value. We get an electron charge that is within 1 standard deviation of the accepted value. And the largest sources of error are the radius, which accounts for 65% of the uncertainty, the plus minus 0.5 variation in the magnetic field, which accounts for 33% of the error, and the remaining 2% is the energy calibration and uncertainty. So conclusion is that relativity wins. Thank you. Questions?
How do you determine the
So, right. So what I did for the errors is that for each of them, I set the other uncertainties to 0 and did the fit again using only the uncertainties from each of these. So I said, what happens if the magnetic field has 0 uncertainty and the kinetic energy has 0 uncertainty? What do we get for the overall uncertainty? And it was about 65% of or the ratios between the uncertainties that you get for doing those for each of these 3 things came out to be these ratios. Yes. So what I did was So what I did for these is I left E over M. So I left E over M as a fit parameter in addition to these whatever else I was testing here, and what I looked at then to see which of these are reasonable things was what the residuals looked like.
So in other words, you're using that 1 more degree of freedom in your set.
Yes.
By varying whatever it was you were testing that
Right.
was your apparatus.
Or 2 degrees of freedom for the linear fits on the magnetic field. Plus the extra fit parameter or for the E over M. Wait, where did I say that? Right. Yes. Wait, did I? Hold on. I'm trying to remember which one I did. It's because I did this a while. It's possible that I did it that way. So I don't actually, the value that I report for E over M is leaving them all fixed. And then the values that I report for charge and mass are uncorrected values because the uncertainty from that is so large that if you add in the uncertainty from the magnetic field, you don't really get any information. It tells you that you're in the right order of magnitude for the magnetic field, or sorry, for the charge and mass. So the magnetic field correction doesn't have any observable result on the separate electron charge and mass values. So these are, right, so the errors that I quote over here, these are in the uncertainty in the calculated value. These are not looking at how far off it is from the accepted values. So the B field would probably be the largest contributor if I did an analysis that was able to tell me why it's off from the accepted values.